So we have seen that performing these atomic read-write operations on the lock repeatedly, even while waiting for the lock, is inefficient in terms of energy, and it actually slows down the thread that is in the critical section. We want to make this more efficient, and one way of doing that is to do a so-called test and atomic op approach in the locking function. So the original approach to using, for example, an atomic exchange is to set R1 to 1, and as long as R1 is 1, try to swap it with lock var. Eventually we see a 0 and we exit. But as we now know, this keeps invalidating everybody else who is waiting on the lock, so we are getting a lot of cache misses while waiting. And active waiting like this is not only spending energy on the bus transfers all the time, but also keeps the bus busy so that useful work in other threads that are not busy waiting is slowed down. So this is kind of like a repeated atomic op approach. To make it more efficient, what we do is we do the same type of looping here, but we don't immediately try to swap. What we do first is use normal loads to wait for lock var to become 0. So the idea is that we're using normal loads while lock var is busy. If we observe that it's free, we try to grab it by doing an atomic exchange. We cannot try to grab it using the normal store. That's why we have to do the exchange. But the idea is that there is no point in trying to do the exchange unless the lock is actually free. And the purpose of the exchange now is solely to ensure that only one of us grabs the lock once it becomes free. But the busy waiting while the lock is continuously free is done using normal reads. So now if we have core 0, 1, and 2, and core 0 succeeds in doing an exchange and gets the lock var in the modified state, core 1 will now reach this point and read lock var, see that it's 1. It's done using a normal load. So here we move to the owned state, here we move to the shared state, and there is a cache-to-cache transfer here. Now we will keep doing this, but we'll keep getting cache hits, so we no longer access the bus while waiting. Similarly, core 2 will load the lock var. It will also get the value and have it in the shared state. And now it also gets cache hits while waiting. So as long as core 0 keeps the lock busy here, these two cores are no longer generating bus traffic. So core 0 basically gets the entire coherence bus to itself, so it can very quickly service cache misses, and cache hits here are much more efficient than bus accesses. And this is going to continue until core 0 releases the lock, at which point there is an invalidation, and these two will read again, see a value of 1, try to compete for it using the exchange, and so on. But those bursts of activity really happen only when they're actually trying to acquire the lock. As long as the lock is really busy, they just keep using normal loads in this loop. So this is much more energy efficient.